Okay, so this is joint work with Ori Rotenstreich, who's currently at Princeton, and Professor Yoram Moses, who's from the Technion. Software-defined networking is an architecture where you have a centralized controller that frequently sends network update messages to switches. Each of the SDN switches is a set of one or more flow tables, where each flow table defines how packets need to be processed. And often flow tables are implemented using TCAMs. A TCAM is a memory for very fast searching, and each bit in the memory can have three possible values: 0, 1, or don't care. In order to understand the motivation, we discussed two interesting scenarios. Atomic bundles is one scenario, and the idea in atomic bundles is that you have a set of updates that need to take place on an all or none basis. That means that every packet that is received by the switch needs to be processed either by the old configuration before any of the updates takes place, or by the new configuration after all the updates of the bundle take place. Now, the main challenge here is how do you implement a bundle in a way that is truly atomic. Now, the second scenario is time-based updates, and one of the interesting features in SDN is the ability to change the paths in the network dynamically based on the network load. So, for example, if you want to change the paths from the before to the after configuration, you may have a temporary state where some of the links are congested. However, if you change the configurations of all the switches at the exact same time, you can avoid congestion completely. So it's an interesting observation that accurate time can be a very powerful tool in network reconfiguration in general. We defined an extension to the OpenFlow protocol that allows time-based updates, and this extension is already included in OpenFlow 1.5. But now the question here is, even assuming you have perfectly synchronized clocks in all the switches, how do you guarantee that updates are performed accurately at the time they were supposed to be performed? So in order to address these two scenarios or two challenges, we introduce time flip. Time flip is a time-based TCAM lookup, and the idea is that in conventional TCAM lookups, you have a search key, and the search key is compared with all the TCAM entries. If there's a match, there's a corresponding action that takes place. In time flip, you have a timestamp attached to the packet's metadata, and the timestamp is used as part of the TCAM lookup. So the TCAM entry includes the timestamp. A time flip is a TCAM rule that uses a specific timestamp value. So that allows you to define a time range in the TCAM rule. So today, off-the-shelf switches can be synchronized very accurately. You can synchronize switches in a network to a degree on the order of 1 microsecond. You take that high accuracy, you combine that with time flip, and together you can get a very accurate mechanism for scheduling network updates. Atomic bundles can be implemented with time flips, and the idea is that each of the individual updates in the bundle can use a time flip. So for all packets arriving before T0, all the bundle updates are disabled. And for all packets arriving after T0, all the individual updates are enabled. And that way you get an all or none behavior like we required earlier. Now, time-based updates can be implemented using two TCAM entries, two TCAM rules, where packets arriving after T0 match the first rule, which includes the time flip. And the first rule corresponds to the after configuration. And packets arriving before T0 match the second rule, which has don't care on the timestamp bits. And this corresponds to the before configuration. So this way we have a very clear distinction, a very clear transition at time t0 from the before to the after configuration. So when we say timestamp, what do we mean? The IEEE 1588 standard defines time of day to be 48 bits of seconds and 32 bits of nanoseconds. And this sums up to 80 bits. Now that's a lot. So does that mean that now if we want to implement time flips, we need each and every TCAM entry to include a very large number of timestamp bits? And if we want to implement a time range, we need a large number of TCAM entries to implement each time flip? The answer is no. And one of the main goals in this paper is to show that a time flip can be represented efficiently using a small number of TCAM entries and a small number of bits in the timestamp field without compromising the scheduling accuracy. To implement efficient time flips, we use two interesting principles that are unique to time flip. One of them is called the scheduling tolerance, and the other is periodic ranges. So to explain these two principles, we discuss this example. So consider a first grade school teacher wants to schedule an afternoon lesson, and it's very important for him to be punctual. So he makes all the students synchronize their watches to his own, and he makes the students write down the exact time at which the lesson is supposed to start, because he wants them to remember it. Now at first the teacher considers starting the lesson at this time. This is the date and this is the time. But then after thinking about it some more, he realizes it's a large number of digits and it's going to take the young students a long time to write down all these digits. So he realizes that by being a bit flexible, he can give up on some of the digits without compromising being punctual. So in our context, we call this property the scheduling tolerance of the system. And the idea is that the controller can select the time t0, which minimizes the number of TCAM entries required to represent the time flip. Now, when the student receives this information, he thinks, okay, I already know the date, so I don't need to write it down. All I need to write down is the time at which the lesson starts. So we use very similar logic, and we call this periodic ranges. The idea is that if we have a time range in the TCAM, and some of the most significant bits are known from context, we can just assign don't care to these bits, which creates a periodic time range. So one of the results that we show in the paper is that if the scheduling tolerance is high enough, you can actually represent the corresponding time flip using a single TCAM entry and a single bit in the timestamp field. But even if this condition is not satisfied, we show that time flips can be represented very efficiently using the two principles we discussed. So that all sounds good in theory, but the question is, would it ever work on a real switch in production? And the answer is yes. Okay, so we've experimented on a real switch. This is a Marvell DX packet processor switch silicon. And we show in the paper that time flips can be performed with a sub-microsecond accuracy on existing network equipment. More details in the paper. So to summarize, basically we used both experimental and simulation-based evaluation to show that time flips can be represented efficiently. And in order to implement efficient time flips, we used two principles we discussed earlier: the scheduling tolerance and periodic ranges. And time flip addresses two interesting scenarios. One of them is atomic bundles, and the other is time-based updates. And finally, the main thing to remember here is that time flip is a practical and efficient method for scheduling network updates. Thanks, with 5 seconds to spare.
Okay. 5 seconds of questions? when you do time-based update in the SDN, you have a problem that the packet arrived to the network, it starts going, and then now it's time for update, but the new path didn't go through this place. So you want a global change in the network to occur, and when the packet already started to go into the network, it should maintain the path that was before the change. So when you do a time step-based operation inside each one of the router, you can get a global state.
So you say that...
You have to repeat the question.
Okay, so what Dan is saying is that not in all cases a simultaneous update is what you actually want. In some cases, if you have a simultaneous update, it doesn't guarantee consistency in the path forwarding. And that's true. Okay, the specific example we gave on one of the first slides is an example where simultaneous updates are the optimal solution. In some cases, you don't want a simultaneous update, but you can use time to set the order of updates. Okay, if you know the specific order in which you want the updates to take place, you can use the time-based operation to do that.
More questions? Okay, so let's thank Tal again.
Thanks.